Welcome, everybody. This is our 11th Hackaday session on quantum computing. And for new communities joining us 2 weeks ago, that's the third session. And for people who are new today, this is where we post everything, all the information and the class. I update with comics every week. So on Hackaday comics introduction to quantum computing, you will find all of the recordings from past sessions. Every Sunday we meet for 30 to 1 hour. Usually I try to keep it within 30 minutes to discuss a concept. And then we can answer some questions and do some discussions after that. We also use the Q-Sharp documentation on the Microsoft documentation website and the quantum katas for our coding exercise. Last class and 2 classes ago, we discussed superposition. And this picture shows you kind of a landscape for learning quantum computing. You can go pretty far with the Q-Sharp exercises, learning the concepts, and go to all these linear algebra or algorithms that you can express using the quantum language Q-Sharp. So today we're going to discuss this very exciting and interesting subject, interference, and that's built onto what we learned so far. So mainly superposition concepts. For people who have been to this Hackaday classes, this will be a revision, but I will also show you some of the new pages and talk a little bit about physics too. Just a step back, looking at what we discovered in the past 2 classes, the quantum bits and superposition. So you should know that a qubit can be expressed as a vector, which in turn is also a superposition of these 2 states, 0 or 1. Each of them would have an amplitude associated with them, telling you how much of the 0 and 1 are in the system. All you need is that you will have this normalization condition where no matter how many states you have in your system, their amplitude squared needs to be add up to 1. So some examples like how you can use a metaphor to express qubits. You could have probabilities of 1/3 and 2/3 coexisting, and you can have probabilities of mixed colored beads or spinning coins with half and half probability of landing on head or tails. So this amplitude square means probability of each state. And when you have multiple qubits, you would just add all of them up. That's why it's called superposition, which is also a linear combination of these different states. Each of them will have these amplitudes, and you just time them, square them, and add up to 1. As you grow your qubits, number of qubits, the possible states that could be in your system grows. When you have lots of qubits, you would not just keep writing all the outcomes. You would just use a summation to say that I will sum up all of the possible configurations in my system, and each of them with an amplitude. We mentioned that the amplitude can be any number. It could be real numbers like 1 to 1/2, 1/3. They could be negative numbers, but they could also be imaginary numbers. So in general, they can be complex numbers. The amplitudes can take all these different phases, the forms. So then some people, I'm really glad that Olivia, I think that is who asked on Hackaday comments. So if we want to have amplitude square equal to probability, how do we deal with the case when you have a imaginary number? You have this I here. I'm really glad that she asked that. So we will take a look today. How do you express complex numbers? This you have also seen in the last class when we wanted to show a qubit as in a three-dimensional space. But we're not talking about qubit right now. We're talking about complex numbers. When you have just real number, you can express it in a line. And the length of that just indicates how big your number is. But then when you have complex numbers, you give it a vertical axis. Then you can express a complex number as an arrow in a two-dimensional space. This we have seen last time. And you also see that it will have a length. It will also have a phase if you are measuring its relative position away from the x-axis. So I show in this new page here, you can actually express your complex number in two ways. One is with this Cartesian coordinate, so x and y, and you have these a and b. So real number is in your x-axis and imaginary number is in your vertical axis. So where this arrow is basically expressed as this projection onto these two axes, a and b. But you can also write it in this polar coordinate, which has a length r and a phase phi. You can express r and phi in terms of a and b and the angle in this diagram. And you will see that when you're trying to calculate the amplitude, you're actually doing a modular square. So is absolute value square. But then you all quickly see that because this phase here, when you do a square, is doing a cancellation. So it cancels itself out. What it leaves is just the magnitude square. So basically, if you have any amplitude, which can be your quantum state, then its probability is just the magnitude squared. You don't have to use a polar coordinate to calculate this. You can also just use a and b and see, oh, actually, r is always positive. And squaring that, you get a positive number. So probability can never be a negative number. That's that. And then what's the significance of having complex or negative amplitudes? From our daily experience, we have seen a lot of different kinds of waves. We have sound waves, light waves, water waves. That's in our everyday experience. We already know that if you have some wave, two waves having amplitudes in phase, so they would sync up and add up. So the amplitude overall will grow. But there are also cases where they can be out of sync and they would subtract each other and you get nothing. We know that amplitudes can add up, which is called a constructive interference, or amplitudes can cancel each other out. This is a destructive interference. So this happens in our quantum mechanical system. And in quantum computing, that's actually what we deal with. Because we can express our qubits with the amplitudes, then there must be interference going on in our qubit systems. So in quantum computing, we deal with probabilities. But classically, we deal with absolute numbers. So if you now use that interference argument and to look at our systems again, mapping your way of understanding in terms of these tree diagrams. This is what we learned as kids, like how do we calculate probability? Classically, if you want to know, say, tomorrow has equal probability of getting a sunny day or a rainy day, what is the probability of the day after tomorrow being sunny? If we were in a classical system, then we would just add up the probabilities. So we need to first time down the tree, and we time all of these possible outcomes being sunny. So 50% times 30% plus 50% times 90%. These numbers are just made up, just any number, but probability, they're always positive. So you get a 60% case in a classical system. But if you want to solve this in a quantum system, or if your system is quantum, there's no reason we cannot give your system a minus sign. And what that does is I just arbitrarily put a minus there. And because we're dealing with amplitude, we will label the amplitude the square root of the probabilities. And I can arbitrarily put a minus sign there. What that does is, even though you have an extra path to get a sunny day, that negative sign actually can subtract and reduce your probability of having a sunny day. This is what's really weird about quantum system, is that even if you have more ways to get to where you are, it could play a negative role. So this example turns out to give you 8% of getting a sunny day. This is what happens when you want to do a measurement on your system, is the amplitude that does the constructive and destructive interference that leads to your result. So if you're observing certain results in a quantum system, that means that that particular result, before you measure it, it would have constructive amplitudes all adding their probabilities up. So the other possible outcomes are eliminated by those destructive interference. That's why you do not measure those unlikely results. And that's what we get in measurements. To have a little bit more, to read a bit more formal description of that classical and quantum probability theory, Scott Aronson has given quite a lot of interesting write-ups and lectures in his own words. So I recommend you to look it up. And it is called a 1 norm for the classical case and 2 norm for the quantum mechanical case. So we will not go into too much depth here, but the point here is that we are dealing with amplitudes in quantum systems, and the amplitudes can be positive, negative, or even complex. And that's what leads to interference as well as measurements. It's not just something that we cannot observe because quantum mechanical systems typically are in very small scale and very cold, but there are actually measurements that we have observed that's directly expressing this interference. For example, this double slit experiment that is very famous. You probably heard of it sometime in your study. There, you can create an experiment that you would have 2 slits letting electron beams to go through. And we know electrons are intrinsically quantum mechanical particles. They will behave in a quantum way. If you close one of the slits, you would get this distribution that most of the electrons would appear close to the slit in the center. And you would think in a classical way, if this slit gets open, then you probably would see 2 peaks like this. But that's not what happens. What happens is that these 2 beams will interfere with each other. And it could even have these destructive interference very close to where the slits are. And you see a dip. And in the center, where they have constructive interference, you will see most electrons. That's really cool. That is a direct manifestation of quantum interference. And we conducted an experiment to discover this. Whenever you have a qubit, a quantum system, when you're doing a measurement, you're actually observing this interference effect. And measurements are not reversible. Like our previous metaphor, if you had a spinning coin, you wouldn't know which side it will land on, and the measurement is kind of knocking it down and doing a measurement. Once it lands down, it would not be able to reverse back. So that's what happens. Say you have a quantum system with 2 qubits, and you have these 4 different possible states. Each of them has a amplitude describing them. Then if you do a measurement, measure the first qubit, and find out that it is 0, that means it will be these 2 states that's contributing. So you kind of eliminated these 2. And you know that the probability of having the first qubit to be 0 will be the C00 square plus C01 square. And after this measurement, you haven't done anything to the second qubit yet. You would then come to a new quantum state that would be these 2 possible states adding up. And you have to keep the probability sum to 1. That's why there is a square root of p now to normalize your system. So this is what happens after you measure the first qubit. If you then measure the second qubit, then it would be either 0 or 1. So if your outcome is 0, then it will be this state that is contributing to your measurement. And you would know the probability will be calculated from the C00. That's what measurement is. And we should do some exercises. We have a very good exercise already that makes a quantum random number generator. So think about the qubits are actually intrinsically random number generators, because if you have a qubit with unknown amplitudes, you can do measurements. And if you have like a fair coin, it can land on either head or tail. So if you have a qubit that can either come out as 0 or 1 with unknown probability, you just keep measuring it. So every time a random 0 or a 1 will come out. That's an intrinsic random number generator. So we actually have an exercise on this on the MS Learn, Microsoft Learn website. Go there, take this class at your own pace. This is a very, very interesting, very fun project that also teaches you how to set up your computer's environment and write Q-sharp programs using the quantum development kit. So we would not use our class time to do this. So, but then this link is here is for you to run it on your own. Okay, so the double slit experiment is one of the examples, one of the experiments physicists in the early 1900s and later did to discover there's quantum effects. And there are a lot of other experiments that people did that really kind of lighting up the whole physics field, that there's something new that we didn't know about. So we'll not go through these experiments, but look them up yourself. All these effects that demonstrated quantization of energy, and they discovered wave-particle duality. Double slit experiment was one of the experiments, and there were a lot of other evidence that they gathered through their experiments. That's what helped physicists realize the new fundamental effects that they didn't know about. And they also led to the mathematical description of the quantum mechanical systems. And Schrödinger's equation was then invented or derived to explain these effects that they observed. So Schrödinger's equation, if you look at the form here, it looks like a wave equation. It's got this delta derivative of function here, and then it's got a time derivative of the same function. And this here, V here is just an external potential. Sometimes you don't have this term here. But if you just look at the form, it looks like a wave equation. And then they must have wave solutions as what called wave functions. The derivation led us to know that the solutions would be a linear combination or superposition of all of the possible wave functions. So very rigorously, you can derive this result out. And that's why in quantum computing, we're using the fact that you can have two, or if you have one qubit, you can have two different possible states in superposition. Whereas in nature, you can have all those infinite number of possible wave functions in superposition. So in quantum computing, we're basically just using two states to be our units, to be our basis for computation purposes. And Dirac comes along and try to simplify things because wave function can be really long, and you can write these amplitudes in terms of the overlap between these this one possible outcome with the overall wave function. And then that's how you can calculate what the amplitude would be. And Dirac came up with a simple notation called Dirac notation that would just be shorthands of these integrals. This is the overlap integral between this one of the solutions with all of the solutions. That's why we have been using this symbol. I didn't really introduce at the very beginning, but now we know. I was just using them as symbols and it didn't stop you from understanding. But now we know where it comes from. This is a shorthand for wave functions. This has a name. This is called a kit, which is a second half of the bracket notation. So this part is called a bra. But what it is a complex conjugate of the wave function. So for physicists or for people who have learned physics, you have seen this. And this is how you would do an overlap integral to shorthand this mathematics. And for people who have seen the hardware class that I have given, I have showed some parallel comparison between many different systems in our universe that actually behave very similarly. So people who have seen this commented last time that this was very beautiful. So this now today we have more examples. So this is showing the Hamiltonian of all these different systems, pendulum, weight on the spring, or LC circuits. This is a superconducting LC circuit, which is used as a unit for possible kind of qubits, also experimentally. We also have nucleus. If you look at their energy or Hamiltonian, they are kinetic energy plus potential energy, and they have terms that have very similar mathematical looks. So learning physics is basically learning all these systems as a model, and you will see how similar different systems are. And the similarity with wave equations, what led physicists early, like 100 years ago, was they measured particles and found they look like waves, and measured waves and found they look like particles. And that's why they could write things in terms of wave equations, and which is Schrödinger's equation. And then they figure out the solution must have our be wave functions. But before this class, we've already been doing quantum computing. We've been doing gates and vectors and all that. We did not need to use any of these. In a way, we are figuring out the best way to teach people about quantum computing. We don't even have to go to physics. So you don't have to know a lot about physics to start working on quantum computing. But it's still very beautiful to show you that they all have physical roots. And if you look at classical waves, they have this wave equation. You can figure out what the velocity of your propagating wave is from just by looking at the wave equation. So in parallel, we have electromagnetic waves, which are light. And electric field and magnetic field, you can also express these. And these are derived from Maxwell's equation. By the way, yesterday was Maxwell's birthday. And these are the 4 Maxwell equations. If you rearrange them, you get to this wave equations. And then you look at quantum waves, these are Schrödinger equations. So they have very, very similar. They're basically all wave equations. And then you can figure out the wave velocity. And this is how Einstein got the inspiration when he looked at the Maxwell's equations mashed up into this wave form. He saw these constants here, permittivity and permeability of vacuum, and they're constants. And he looked at the classical wave equations. This gives velocity. That means these 2 constants give you the speed of light in vacuum. That let him figure out the speed of light must be a universal constant, and which then also led him to develop relativity. So this is what's really beautiful to look at history and how physics was developed, and how just by looking at dimensions and units and equations, you can realize a lot of insights about nature. But again, you don't need any of this to do quantum computing, but I still like to show you. This is what you need to know about quantum computing, is that amplitudes can be negative or complex, and they can do distractive interference. Okay, so that's what I want to show you today. We have this survey on Microsoft Quantum Development Kit website. And this is really for you, an opportunity to let us know what are you looking for, why are you learning quantum computing, what do you want to learn next, so that we can develop official materials to provide you. Also, some really fun activities going on. Dr. Sarah Kaiser, by the way, I got these Q-sharp earrings from her. She's doing these live coding events on Wednesday and Saturday on her Twitch channel, so check them out. And we also have these coding contests going on right now. Register. There are already some sessions, like exercises posted, so you should take a look and have fun with it. And here are the links where you can find all of the information, and the class is recorded. You can find the past recording and slides on this link, and the videos are also posted on my YouTube.